some of the things about validation have already been covered, which is really great because actually validation is not something you should wait until the end to do. You ought to be doing it all along, and that's even more true at cryo-EM resolutions, or 2.5 to 4 angstroms, than it is at higher resolution, as Pavel had pointed out. So this has been a big change and a real effort for us because our malprobity tools that are completely integrated into Phenix work really well up to about 2.5 angstrom resolution. And now, particularly because all of those validation tools are now being refined, as again, Pavel pointed out, they're not actually useful at all, really, to validate most of the cryo-EM models. If you have a perfect score, it really doesn't mean anything. If you have validation outliers, you should still try to correct them, but often you won't. And it means that you really have no idea how good the structure is. And so we've been working very hard for a number of years now to try to develop tools, and a lot of other labs have as well, that can still work at those resolutions. And so there are mostly things that are multi-residue validations, and certainly things that are, I'll explain how the traditional tools work first, and then I'll show you new tools and how you can use those. And this is still a work in progress. We can't fix everything. You never can fix everything, but it's proceeding, and there are a lot of things that can help you. So one thing to say is that you don't always have to be at high resolution and completely accurate to learn really neat things. So we've had a lot of fun, for instance, looking at and also trying to fix up the new SARS-CoV-2 structures. And they've shown really amazing, completely unexpected things, like this neat structure of the RNA-dependent RNA polymerase that now for the first time shows what happens when it's really working and it has a long product RNA, and these N-termini from the NSP8 fold up into this very long helix and help hold the RNA. And so that's something how the virus deals with its very large genome. But if you're really serious about drug design or specificity of binding or chemistry and catalysis, those really require accurate atomic detail. And so ideally, you would try to get to 2 angstroms, but when you can't, you can at least make the detail better at 3 to 4 angstroms. And we'll try to lead up to how to do that. So the malprobity criteria started off with all atom contacts and class scores. We developed updated and criteria for things like Ramachandran and Rotamers and geometry, and new ones for RNA backbone. And now for lower resolution, we have other new tools. These all need to work together. So they had to be modified a little bit to work well together, but this has been working now for quite a while. And there gets to be more, not only more and more data in the data bank, but much more accurate data. And it doesn't work to just filter files by resolution. You have to look by residue, because even in very high resolution files, there will always be some parts that are disordered, or ones where you see so many alternate conformations that you can't really actually fit them as accurately. So there's sort of a sweet spot. If you ever had a choice, go for like 1.4 angstroms. there you can't see too much detail to get confused, and everything looks gorgeous and you can really see all of it. So if cryo-EM ever gets down to that, you can remember that. So our starting point is that most structural models are missing half their atoms. Those are the hydrogens. And they're also what makes all of the contacts, or about 75% of the contacts in a protein and a little less in nucleic acids, have hydrogens on one side or the other. And so if you want to have accurate contacts where you bind ligands or other molecules, or even inside of the molecule where the folded form makes good contacts, if you don't have the hydrogens there, you get it wrong. And most of them can be added very reproducibly from the heavy atoms. And our program REDUCE, that's been mentioned before, works very hard at trying to get the ones that are rotatable correct. We look at entire H-bond networks and optimize the whole networks. Again, nothing like that is ever perfect, but it's very good. And so the way these work is that we add the hydrogens and then put van der Waals shells around them, which are the little gray dots. And then we look at how those van der Waals shells interact with each other. And so we do that by looking at a very small probe. It's only 1/4 angstrom in diameter. And we move it around all the van der Waals positions that are not hidden by covalent bonded atoms. And we see whether it touches anything else that's not covalently bonded. And where they touch, we start showing dots. First, they're blue at a 1/2 angstrom contact, and they get green at optimal van der Waals. And then if they overlap a little bit, they start getting yellow and being spikes. If they overlap a lot, they get really painful, bright colors and long spikes and look uncomfortable. We may have overdone that, but anyway, the clashes do look uncomfortable. And if they overlap as H-bond donor and acceptor, so it's a good overlap, then they make these nice, calm, pale green hydrogen bond dot pillows. And so what makes us believe this is that in the good parts of really high resolution structures, the hydrogens interdigitate with each other beautifully, and they make contact almost all the way around. If this weren't true, we wouldn't be doing all of this. Of course, it's not perfect. The atoms aren't completely spherical, and you can get some cases where you get some small real overlaps, but they're almost always still in the yellow, which we don't count as a serious clash. And using these contacts is really valuable for getting local conformations correct. So for instance, here's a histidine that's at the active site of this structure, and it's got 2 really horrible clashes. One is to a water where you could imagine the water may be wrong, but the other one is to an obligate acceptor, that carbonyl oxygen on the backbone. And if you flip this histidine, which is, it really looks about the same in even quite high resolution density when you flip it, but it exchanges carbons and nitrogens. And now you get 2 beautiful hydrogen bonds. And so this kind of change doesn't change the fit to the density, but it enormously improves the local chemistry and interactions. And so it's a pretty clear win. And these can be done automatically even without looking at the map at moderate resolutions. They're still worth doing at lower resolution, but they're not going to be nearly as effective because the contacts may not be in quite the right place. So Molprobity has a lot of different markups for various mistakes and for outliers. Outliers are not always wrong, which we'll come back to later. So bond lengths and angles have these springs and sands, and bad rotamers are in gold, Ramachandrans are in yellow. The clashes are really important, and the H bonds also at low resolution. One of the things that happens often at 3 to 4 angstroms is that you get many fewer hydrogen bonds than you should. And that's also a bad signal, even if you don't have clashes. Then we'll say a little bit later about cis-non-prolines, which are extremely rare, and they're flagged by these sort of webs that enclose the backbone between the two C alphas. And we'll briefly mention ribose puckers, which can be corrected by a simple algorithm for RNA. It unfortunately doesn't work for DNA. And we'll particularly be talking about Kablam outliers, which are marked between adjacent carbonyl directions. So this is just to let you know things that will show up in my later slides often. My advance is not working. Sorry, the PowerPoint has stopped letting me advance. No.
Try the arrow in the bottom left-hand corner, Jane, now that your mouse is moving.
Oh, all right. That worked. Okay. All right. Thank you. So, as I said, at higher resolutions, sort of anywhere around 2 angstroms up to about 2.5, this process really works. If you get rid of almost all the outliers, you really do have a better structure. And for instance, here's just one example where there were a bunch of clashes and waters that really were ligands and so on. A lot of changes here, particularly in this region. And the result of fixing these things, actually in this case, it lowered the R free by 4%, but that's unusually good for that. But this is clearly an improvement. And in general, people have been able to make use of this. And over the years, before molprobity to now, it's sort of leveled off at about as good as you can get easily, pretty close to what's in the good structures. And it's only about 1/3 as many clashes and other outliers as well. So that's been really great. However, people have learned to rely on this. And as I said, it doesn't work as well later. However, all of those early tools are there in the validation GUIs, either the X-ray one or the cryo-EM one. And as Pavel said, you can get to it either on the validation tab or on the cryo-EM tab. And he showed a lot of these, so I'm not going to dwell on them much. But again, you have this summary, and in this structure that's being shown, it does actually have a lot of outliers. It's not a brand new structure, and apparently they weren't all refined away at 3.8 angstroms. And you can look at the model with the molprobity tab, or the model versus data, or the data, and just a few of the things in data and in model versus data. Again, those have been talked about already. And so under the molprobity tab, you have 6 different things, geometry restraints, even at higher resolution are pretty well restrained, but particularly at lower resolution, you really want to have tight restraints on the geometry. And that doesn't get you in trouble because for the most part, there's only one value. For bond lengths and angles, there isn't some other angle that you could go to that's way different with a barrier that could be wrong. You're just making tighter the agreement to what you know is the unstrained answer, at least. You can have strain put on it, of course, in the structure to pull it away from that somewhat, but it should not, just from the strain, get bad enough that it will be an outlier. When you get an outlier is when you have something turned around backwards or in the wrong rotamer or the wrong Ramachandran, and then refinement is sort of stuck. It puts a lot of that strain, particularly into bond angles. Bond lengths are usually tight enough that they don't change very much. And so some of the more interesting ones that also have already been mentioned are Ramachandran, and the GUI has chi1, chi2 plots, and that's great for some of the outliers. We're trying to develop ones where we can really show plots for the outer chi angles. But you can see in this case that the rotamers were being restrained pretty tightly. I mean, here, for instance, it's very much inside this commonest rotamer. There are two rotamers, the MT and the TP, that take up about, I don't remember, 95% of the leucine rotamers. And they're in the data, they're much broader distributions where they're not restrained. And so restraining them is fine, except that you have to be sure you're in the right one. It's a bit like the Ramachandran problem, that there are some tools in the real space refinement in Phenix where you can actually optimize whole sets of rotamers against each other in a local group. And you can also make small adjustments to the backbone, which you need to do to really fit them. And those are very much worth running before you refine with restraints on the rotamers. Although actually in that case, it doesn't matter that much because there's a small finite list of rotamers to look at. And so you can actually combinatorially look at them for rotamers, which you can't really do very well for Ramachandran. And then the Ramachandran plot for this structure is very strange, with lots of rotamers around the edges in weird patterns. And apparently they didn't know about the Ramachandran plot for ILU or Veil in the program that was used for this, because it has quite a lot of outliers, particularly on the right-hand side of the Ramachandran plot, that those branched beta carbons really hate. And so this plot gets a very bad score on the Ramachandran Z-score that Oleg developed. So what I've been emphasizing all along in this talk is that we need completely new ways to do validation once we get to 3 angstroms and worse. And so the question is, why does this happen? And what are we and other people doing about it? And where are we at this point in helping you to do real validation that will help you make corrections? So the most common problem at 3 to 4 angstroms is that you can't anymore see a protrusion for the carbonyl oxygen. So at high resolution, those oxygens stick out sidewise from the tube of the rest of the density. But at 3 angstroms or lower, they just fade back into the tube, and you can't really tell from the map which direction the carbonyl oxygen is going. And that's bad because that's the main key, that and the C beta, are the keys to how you fit each peptide. And when you get the peptides oriented wrong, it hurts everything else about backbone conformation and even side chains. And so one way of putting this is that at 3 to 4 angstroms, many different models are equally compatible with this broad density. And even multiple models that have good geometry, but certainly if you don't put some restraints on, definitely there are a lot of things compatible, and you can even get the chain going the wrong direction if you don't know which way it should be going. And so probably things will go toward ensemble representations, and people are trying to do that. The only method I know of so far that really does a good job of using ensembles to show uncertainty is this system of ribosolve, which is from the same lab that did Eraser. They've used it for RNA-only models between about 4 and 10 angstroms and can do a very good job of determining the overall structure. And they also show you that they don't know the details, which is really nice. It's good, very good for the end user, but it's also pretty good to keep the structural biologist honest about what inferences you actually can make. And so these pictures work very well. Nobody has really developed a good way of showing enough uncertainty, but not too much at 3 to 4 angstroms, but we'll get there. So one of the issues that we try to address is that there's some sorts of errors that are just one-offs. You did something weird, there's something very peculiar about your structure that didn't really work with standard methods or whatever. But the ones that we try to target are systematic errors where either programs or people do the same wrong thing a lot. And so if you figure out how to flag that and particularly how to fix it, then that really has a lot of leverage on improving the structures. And the flips, the backward C-beta branch side chains and clashes and hydrogen bonds, and we'll briefly mention cis-non-prolines, and then actually say a good deal about this KBLAM tool, which looks for incorrect carbonyl directions. And so again, just to show a specific example, at these resolutions, you can have serious errors by some criteria, and particularly the new criteria. So here in the middle of a helix is a cis-non-proline and a Ramachandran outlier and a Ramachandran disfavored and a really bad clash. But there are no Ramachandran outliers in here. The structure looks great by the old-fashioned criteria. And so what's going on? Well, again, it's peptides that are misoriented, and often when they're bad by almost 180 degrees. For instance, some of you may know that when you have a tight turn, they're 2 good conformations and they orient the peptide oppositely. And very often, if you try to actually turn a peptide, it gets very unfavorable in between, and then it slips into another possibility. And so when you have a misoriented peptide, the phi size on either side of it will be wrong. In the peptide preceding that residue, you'll get the psi really wrong. And in the one afterward, you get the phi really wrong. And so you tend to move on this map either up and down 180 degrees or back and forth 180 degrees, which will take you at least close to the wrong local minimum. So as Pavel said, you want, whenever you possibly can, to find these things and fix as many as you can. You're not going to be able to fix all of them, but you can fix a good many. And they're good clues to which ones are fixable that I'll give at the end. And then you can use Ramachandran restraints. I think it's still better probably to build ideal helices, for instance, and ideal data structure until you can see otherwise in the data, and restrain the hydrogen bonds. Those are a little less likely to go totally the wrong place. So we also have learned a great deal and practiced some of this in the cryo-EM model challenges that the EMDB and particularly the EM data resource have done several of so far, and there's another one coming this fall, where it's a little bit like CASP, except it's not supposed to be a competition, and the targets are not as obscure. But this one particularly, this is the 2019, finished in 2019, which used a number of quite different targets. So a few things that we saw happen. There's this business of structures that have internal symmetry and should really have gorgeous contacts like this one, which is all H bonds and van der Waals, nice, cool blue and green and a little yellow. And a couple of the models look like this, where they obviously hadn't been looking at the neighbor when they were fitting the unique unit. And you can do that for a little while, although I think it's still better to turn on the neighbors even from the beginning, because it's not trivial to fix these large clashes between the neighbors. And then there's some local things that just go wrong, like this backbone traced through the side chains. And so that's really a tryptophan up there, which got stuck down to the bottom in the incorrect model. It really should be this. And so, this is just a local glitch, but it did involve a lot of peptide misorientations, but a little worse than that. And then one thing that you really should worry about is metal sites. And if you know they're there and more or less where they are in the sequence, then they're not much of a problem. If you start to model them in, you can do quite well. But if you have a site in your structure that you didn't know about, then you can get real problems. So this is what this zinc site, it's a 4-cysteine zinc site, nice tetrahedral cysteine links. And if you didn't know to model the metal in there, you can get all kinds of horrible geometry. And sometimes people end up building disulfides between these cysteines that are so close together, which is a very common mistake. There were some of those in the SARS structures recently in really bad density. And then you could even get the connectivity wrong. So this one was traced through the zinc instead of staying in what was really the backbone. That level of thing really causes enough other errors that you can usually spot it. Then there are single problems with carbonyls. So here's the end of a helix, well, the beginning of a helix actually, with the carbonyl pointing in the wrong direction. And actually, if you really look at the density, you can see that it's wrong in this case. And if it gets changed, you all of a sudden get rid of a lot of clashes and kablam outliers.
Stereo.
Yes, this is a stereo picture, so don't worry about it. You can just look at one side of it. And then these sorts of problems even lead to sequence misalignments. So here is a place with a whole bunch of outliers around a term. The magentas are Kablam outliers, and there's geometry as well as cis and twisted peptides. And it really should look like this, and actually use the density at that corner that is even being encroached on by a lysine from somewhere else. But this is obviously not a good fit. But what really is happening here, you have G, Gly, Lu, and Phi, and in the right answer, it's Gly, Lu, and Phi here. It's shifted up by 1. So this is one end of a 1 residue sequence misalignment. And where you actually have density at the ends of a misalignment, things like Kablam and clashes will often show you the problem. It's much harder if, say, this loop were disordered to figure out that there's a sequence shift, because then you really rely on the shapes of the side chains. So this is a whole set of potential problems. And so there are a bunch of new tools being developed to come to the rescue of this. There's markup for cis-non-prolines, and basically, unless you already know that your molecule has one, you shouldn't even try to fit them at 3 angstroms or lower. There's a tool called EM Ringer that I'll briefly say something about, which at the moment is mainly useful as a very useful and sensitive overall quality measure. And Jamie Fraser's lab is working on making it more useful for local things. And Kablam is our favorite flagship thing at the moment. Isolde is one of the greatest ways for going in and correcting things. Undowser isn't very useful at 3 to 4 angstroms, but it is a new function in molprobity that really helps test those waters that you've put in and show the difference between the waters and ions and other problems that waters can do. And we have a new tool that we're developing now that will help model good RNA backbone at 3 to 4 angstrom resolution. So cis-non-proline peptides are very rare. Cis-prolines happen about 5% of the time. And so they're definitely worth modeling and looking for, even at 2.5 or 3 angstroms, certainly. But cis-non-prolines only happen 1 in about 3,000 residues, and they're much harder to see. And so you can see them in cryo-EM maps. For instance, the original 2.2 angstrom beta-galactosidase map. You can tell the difference if you model it the 2 different ways, or even you can get a clue looking at the cis-non-proline, whether it's right or not. And that one's interesting because it does have 3 real cis-non-prolines, 2 of which are at the active site, and another one is involved in binding. And it turns out that cis-non-prolines are about 5 times as common or more in carbohydrate active enzymes. And nobody yet understands why that's true. If any of you get interested in that and can figure that out, there must be some enzymes in the carbohydrate pathways, but this is true in all kingdoms of life, so it's not a simple thing. Anyway, if you're working with a carbohydrate active enzyme, it's worth checking out the related ones to see whether they have cis-non-prolines. But anyway, so there are some real ones. However, there was an epidemic of people using way too many cis-non-prolines for about 10 years, between 2006 and 2000, in our libraries, which were good enough to show things that rare and know that they could be real. And the trouble is, it's worse than random because a cis peptide is more compact. And if your density is patchy or just very low, the cis peptide actually fits the density better, but it's wrong. And particularly if you have 2 or more in a row, they're wrong. And this is true even at high resolution in the bad, the disordered parts where the density is bad. And so this shows the epidemic when, the rate of cis-non-prolines went way up. And by now it's gone back to more or less where it was before, because people know now they're flagged in our programs and in COOT and lots of other places, and most justify fitting them. So this shows EM Ringer, which I mentioned, which is available in the validation GUI in Phenix. I guess it's separate from the validation GUI. I'm not quite sure why. But what EM Ringer does is it looks at the position of your C beta, and it looks around in a ring at where the C gammas would be in the staggered positions. And it makes a plot for the overall structure. These gray areas are around the staggered position at 60 and 180 and minus 60. And you get a good score in those positions in all of your residues. It's actually both a map quality measure and a model to map criterion, because basically if your map is too broad or low or disordered, then you won't get this kind of good staggered distribution positions. But also it is actually a backbone quality measure, because the thing that gets these wrong most often is when the C alpha C beta angle is wrong, and that comes from your backbone misfitting. So it's an overall measure of map quality and of backbone fit quality. So then I've mentioned KBLAM a lot. It got started when we were looking at just diagnosing secondary structures and finding at 3 to 4 angstrom where the helices and strands were. And the typical things people use are Ramachandran criteria and DSSP, which depends on backbone hydrogen bonds. And both of those fail badly when the peptides aren't well oriented. So when you can't see the carbonyl oxygens, these just don't work. Now, actually with cryo-EM, you can do a pretty good job locating helices at 5 or 6 angstrom resolution, or even a little lower. And so actually it's not true that you can find helices better at 3 angstroms than you can at 6, because you see too much misleading detail at that resolution. Because what happens is that at 2 angstroms, for instance, the helix is a spiral and it's 0 density down the middle. And at 5 or 6 angstroms, it's a tube and the middle is the highest density. And at 3 angstroms or 3.5, it's going between those two regimes, and it doesn't do it consistently. And so if you follow all of the detail there in the map, you'll get some of it wrong. And also the side chains in the backbone density start to influence each other more. So what we were used to at 2 angstroms, we'd fit the backbone and then worry about the side chains. And that doesn't work as well. It works better in cryo than it does in X-ray at 3 to 4 angstroms, but it's still got problems. It will still introduce some artifact into that density. So KBLAM uses virtual C alpha dihedrals primarily, which is not at all a new idea. So C alpha to C alpha, that's actually quite accurate the way people fit proteins, even at pretty low resolution. It's certainly not perfect, but it's more accurate than anything else. And so it tells you, should this be a helix or should this be a strand? And then Kaplan measures a virtual dihedral between adjacent carbonyls, and that tells you where you got it wrong. And so this combination is very powerful. And so you can plot these much better in 3 dimensions. So here are the 2 virtual C alpha dihedrals, one coming into the residue and one going out. So it's a little like phi psi, but over a much wider span of the structure. And for these, this is a structure that has really dire helices. That the people who deposited things for helices, and they're annotated in the PDB structure, but they're not at all helical in the actual structure. But they all fall in this red region that is the central alpha helix part. But if you look in the other direction, where this is the carbonyl dihedral, they're more or less evenly up and down the whole span. And these contours enclose the good data, the reference data, quality filtered data from high resolution structures, and they just don't occur in these places. All right, I guess I talked too much at that slide, sorry. And so this just shows for one of those examples, this problem with the Ramachandran. And we went into all of this. Okay, so what you get as markup in King, and it hasn't yet been added to either Coot or Isolde, but it's sort of on their lists. So I hope it will come soon in a program that doesn't show that outlier. It's much harder to fix. But these are really, this sort of shows over here, the C alpha trace is quite normal for helix. It scores really well as being helical. And then there are enough backwards carbonyls that this doesn't look helical at all by Ramachandran or DSSP, but it's pretty obvious what you want to do once you figure out which way this is going. There's so many wrong ones in this little area that it's not very clear. And for instance, in beta structure, again, the really neat ones are where you get 2 Kaplan outliers or disfavored in a row. And in fact, in this one, there's actually this one place with 5 in a row. But when you have 2 in a row, it's almost always the central carbonyl that's wrong. And indeed, in beta structure, there is a systematic error where people sometimes fit 3 adjacent carbonyls pointing in the same direction, or approximately the same, and that's always wrong. 2 in a row you can get, and that's a common way of making sort of a corner in beta structure, but 3 in a row is almost certain to be wrong. And if you flip the central ones, including the inner ones here, then the tight turn looks reasonable enough that you can fix it. And so in Phenix, Kaplan is done as a routine validation now, and you should not ignore it. This is one of probably the most important thing in the validation GUI for either X-ray or cryo-EM at 2.5 to 4 angstroms. And if you pull it up in Coot, this one happens to also have a cis-non-pro peptide, but as I say, Coot doesn't show the validation markup yet. Hope that happens soon. But this one is in the last turn of a helix, and one of the things to say is if you get one of these in the middle of what looks like a straight helix. It doesn't have a big bend in it or a gap or whatever. You always want to fit it as a more ideal helix. And so if you just take that particular carbonyl and flip it over and let everything relax, that's the right answer. Then Tristan's Isolde program is an even better way to fix things like this. It has quite a learning curve, but once you get into it, it's really neat, very effective. And for instance, here's a close-up of, actually, this is a proline that was fit as trans in one of the SARS structures. They knew that they shouldn't have cis-non-prolines, and they used some sort of program that went overboard and wouldn't fit anything as cis. But prolines really can be cis, and you can see them at these resolutions. So this one is particularly nasty because if you look down here, doesn't this look to you like a tryptophan side chain? And this residue 182 is actually a tryptophan, but they only fit it out to the C beta as a stub because if you make this proline trans, you cannot move that tryptophan into this density. But if you make it cis, then let it relax, it slides right into the right density. And also another neat thing about Isolde is that when you first start it up, if you have a place that had a lot of incorrect restraints on it and things where are in the wrong local minimum, you will all of a sudden get lots more outliers when it first starts up because it's running molecular dynamics. And so this is a user-guided interactive molecular dynamics, and it's pretty neat. So here's another example from, this is from the remdesivir polymerase structure in the SARS proteins. And again, just an example of RNA that's very correctable. So it has outlier conformations for one region in what is overall an A-form helix. What?
What's showing on your screen looks like your old system.
It's changed now. It's just very slow.
Oh, okay. Sorry. Apparently it took a while to update that. So now you should be seeing 3 outlier conformations, and this side chain, it is actually fit backwards. It's fit as syn when it should be anti. And over on the right side, you see it really fitting well into its density, and all of these are good conformers, and it really is quite A-form. So one overall real piece of good news from that model challenge and that we finished in 2019 is that none of the targets were significantly lower resolution than about 3 angstroms. And so we had a number of 3 angstrom targets. So statistically, we could compare different methods. And I'm not going to try and explain what the sliders show, but the outcome of that was that there were 5 or 6 different standard methods that do quite a good job at 3 angstroms, and Phenix is one of them. You will definitely get a good overall structure, and it gets a long way toward getting the details right. We're not sure anybody can do that at 3.5 or 4, but maybe they can by now. Methods in cryo-EM in general, including validation methods, change so fast. You know, every month you have different new tools that are better. And then the other take home that our group was really happy about is that we're looking now at a correlation plot where more diagonal ellipses and narrower ellipses are higher correlations, and they get circular and almost disappear if there's no correlation. And so, for instance, definitely Rodimer, and to some extent class score and Rama outliers really solutions because people are refining them. And these are being compared and correlated with measures of match to target, because in the challenge we know what at least an approximately right answer is. And Kablam correlates better than anything else, including resolution and map to model fit. So the statistics are not great on this, so it's not going to stay that dramatic, I don't think. But really, it does work. It actually makes things closer to the right answer when you fix them. So take-home lessons at the end of this. Identify secondary structure early. And in cryo-EM, you might want to go to lower resolution where you can see helix, and you can even do a decent job of finding beta sheet. And if you pay attention to the direction of the twist in the beta sheet, you can even see which way the strands have to go. But anyway, find secondary structure by whatever method is appropriate. Then look for problems in your initial model. So the final result of model building, so I don't mean the very first model, or your first decent model for the good part of your structure. Look for problems in it in validation, and you may at that point even see clashes in Ramachandran and so on. Try to fix as many things as you can at that point, but don't overdo it. You'll never fix everything, and some of them are real hard, and you would actually be overfitting Chandran. Then, as I say, Kablam is particularly useful. Then there are two really easy cases to fix Kablam outliers. If they're inside secondary structure, regularize it. If they're two successive outliers, try rotating the middle carbonyl, which will almost always fix them. And that's a fairly large fraction of the outliers that you will get. Fixing things in loops is possible, but it's harder. So at least do the easy cases before you start refining. So I thought I had another 4 slides in there, but apparently I don't. So I will just tell the message of them. Basically, your goal is not 0 outliers. If you have 0 outliers in a big structure, you've misfit it. You've overfit it. Now, maybe you have to, but it doesn't mean that it's right. You want few outliers, as much as you can reasonably fix and be sure they're better, but not 0. And again, you want to look at all the worst outliers if you can, particularly if they're clustered near each other. There will usually be something that's really in the wrong local minimum that's making multiple problems. Don't expect you can fix every one of them. And also, one of the points to fixing outliers is that rare conformations, if they're real, are usually functional and they're interesting. And so if you can get rid of the noise of having too many outliers, then some of them will be genuine conformations. They're still outliers, but they can be correct. And so you want to find those. And then, as I say, live with it. You will have outliers left at the end, at least if you use things like Kablam. And so these are the current people in our group. Actually, Bradley left a little while ago, but anyway. And Phenix has been fantastic for us, and being one of these teams is great.
Great. Thank you, Jane. Fantastic. if anybody wants to turn on their video and raise a hand so that we can see a hand. If you've got a question you want to ask. There are also some questions in the, well, there's a question that just came into the chat. So for, as an overall idea, what would be a good or reasonable, acceptable and bad KBLAM score for a 3 to 4 angstrom map?
Well, this is new enough. It isn't, for instance, in the PDB validation yet, which it's supposed to be by the end of the year. We'll see whether that really happens. The outliers are defined, of course, by what happens in reference structures. And so the outliers are 1% outliers. So they're more like Rotemers than Ramachandran. Ramachandran has a much lower outlier level because we have a lot more good data for it. So if you have 1% outliers and 5% or less of disfavored, then you're doing as well as reference structure. And so that's clearly a good score. If you're not much worse than that, you're probably fine. And it's feasible when things go wrong to get much worse than that. And so those numbers are not too different from what you see in well, the idea in Ramachandran and Rotemers that they have a favored level, which is 5% for KBLAM at the moment, and 1% for outliers. We're in the process of getting an updated data set that will probably make that a little better. The more good data you have, the better you can get your contours to behave out to very low rates in the good data. So I hope that helps.
Oh, wait a minute. Okay, so there's a question from Joseph.
Yes, so I have a naive question. So let's say if I have a query map at about 3 angstrom, and the most similar homologous model that I can find is already have an outlier 18%. So in this case, should I try to fix the outlier in the homologous model first before I worry about the real space refinement and see, and then after that to fix the model? So
yes, absolutely.
Yes.
You're definitely right.
Yes.
And so it doesn't matter whether they came from your initial model or from somebody else's model. It's still a good idea to try to fix them before you refine it.
If that reference model is much higher resolution than your map, otherwise you're probably better off just fixing your new model.
Yes.
Yeah.
Yeah.
Yeah, there is a point which if the model that you got from somewhere is so bad, you may be better off just trying to interpret your map and build a model if it's good enough to do that instead of using a very bad starting model.
Well, and again, if the outliers are in bad density in even high resolution, you may just want to leave out that part and fit those new. Or if it's disordered in your model, you also may want to do new fitting in that part, but to use the higher resolution model in the core for sure.
thank you.
There's a few other questions in the chat. So if there are any further questions, is it possible to just email you guys whenever? Of course, please. So there's a help at phenixonline.org that you should feel fine to email, and somebody will get in touch.